In the case of real repeated lambdas, we're only going to look at the specific situation where our repeated lambda leads to a full set of eigenvectors. That is, in the 2x2 case, a basis for R2. So this would be known as the non-defective situation. As an example of a matrix with a non-defective situation, here, let's take this example where the lambda of -1 appears repeated twice. So you can, again, pause the video and check that your solutions are going to be given like this form. You'll have e to the minus t with a 1, 0, and e to the minus t with a 0, 1 as the other eigenvector. Individually, the two components, x and y, are given by those two exponential functions. You can reorganize each of these equations for e to the minus t, and you'll find a similar form. From this, you'll get that y is c2 over c1 into x, or y is kx. Now remember, c1 and c2 come from initial conditions. There's no restriction on what those could be. They could be positive, they could be negative, which means this value of k could be any real number. So what happens here is, in the phase plane, all of our trajectories are lines that go through the origin. And you can sketch a variety of lines with different slopes, and you'll end up getting a pattern that looks something like this. So this point at the origin, x equals 0, is called a star node. And I think it's obvious that it's a star because it kind of looks like a star. If the lambda value is less than 0, we get what's called a stable star node. And in this particular example, we have a lambda that's less than 0. It leads to a decaying exponential. And in this particular situation, all of the trajectories approach 0. And that's where the stability comes in. Everything will eventually settle at x equals 0, and it won't be able to leave. And that means all the trajectories go to 0 as time goes to infinity. But the opposite situation is, if lambda is positive, you'll get what's called an unstable node. Now, in an unstable node, all the trajectories leave the origin. So just as another quick little sketch, in this particular situation, all trajectories leave as time goes to infinity. All go off to infinity as t goes to infinity. So that would be an unstable star node. Now, just as a little note, if lambda repeated has only one eigenvector that we're going to call v, you get what's called a degenerate node. Now, without proof, a degenerate node basically says you've got something missing. And if this is the eigenvalue, a degenerate node will lead to trajectories that kind of hover around that line. Eventually, they will start parallel or end parallel to that line. And it's called degenerate because it wants to behave similar to a spiral node, but it just falls short. It's an inferior case. If the lambda is less than 0, you'll get, once again, a stable degenerate node. And if the lambda is greater than 0, you'll get an unstable degenerate node. These are characterized by the fact that these trajectories end up being parallel to the eigendirection. Now, the final case here is when you've got these lambdas real and distinct. And there's two special situations we're going to worry about, is if the lambdas have the same sign and if the lambdas have the opposite signs. Those are the two important situations. Now, in the case of same sign, we'll do this example first. Here's a system, a 2x2 system, where the lambdas are given, and again, they have the same sign. You can go through, solve the full eigenvector problem, and come up with these two eigenvectors themselves. We can call this one V1, we can call this one V2, and in this situation, we cannot eliminate the parameter. And the reason we can't eliminate it is because these individual solutions are pretty complicated. So as an example, the x of t here would be 3c1 e to the minus t minus c2 e to the minus 5t. Y of t would be c1 e to the minus t plus c2 e to the minus 5t. It's hard to unjumble it. It's hard to isolate the t. So instead what we do is we do the qualitative analysis that I mentioned at the beginning. We're looking for the behavior of the trajectories, not a formula. And that's a big difference. We are giving up the hope of trying to find a formula for this. So the best place to start is to take a look at those two eigenvectors and go to the phase plane. Now in the phase plane, we've got our x and our y. We're going to talk about each of those eigenvectors. So let's say here v1. v1 is a vector that looks something like this, 3 and 1. So there's v1, and its eigenspace is a line. It's a one-dimensional subspace. v2 is this vector here, -1 and +1. So it's this diagonal vector there, v2. Its eigenspace is again a line, one-dimensional space. To understand qualitatively what the solution is going to be doing, we're going to take a look at two cases. Now in the first case, I'm going to take the solution, x of t, from above here, and I'm going to factor out one of the exponentials. So I'm going to factor out the e to the minus t. And when I do that, I'll have a c1, 3, 1, plus c2 e to the minus 4t, -1, 1. So all I'm doing is taking this full solution and factoring out one of the exponential terms. And what's important to notice is that there are two terms left here. One of them has no exponential on the inside. The other one has an exponential. This first contribution says, look, as if I were to take t to infinity, I will certainly see that x will go to 0. So that's clearly understood. But if I study this portion now, when t goes to infinity, the term with v1 will dominate over the v2 term. Again, this is our v1 and this is our v2. The reason it will dominate over the v2 term is that this exponential, e to the minus 4t, goes to 0 rapidly. And that means, yes, we understand that the full solution is going to the origin, but as it goes to the origin, all the trajectories are going to be nearly parallel to v1 as x goes into 0. And so regardless of where we start here, as we go and run time to infinity, everything has to go to the origin, but they have to come in essentially parallel to this v1. So regardless of where we start, things will approach the origin and move in almost parallel to v1. In the other situation, what we're going to do now is instead, to complete the story here, we chose to factor out e to the minus t, but if we factor out e to the minus 4t, we're going to get a different story. We'll get a c1 e to the 3t, 3 and 1, and c2 with a -1 and a +1. Now we're going to run the movie in reverse. As t goes to negative infinity, so the start of the trajectories, we're now asking a question, where do these trajectories start? Where do they come from? Well, this e to the 3t will go to 0 when time goes to negative infinity. So at the, quote, beginning, this term with the v2, this is the dominant term. So where all of these trajectories start far in the past is along v2. So trajectories start along v2. So if we were to run this movie fully in reverse and we took a look at the phase plane, eventually we would start from somewhere that is parallel to v2 and move our way to the origin. So regardless of which point we pick, if we run the movie far enough back in time, they'll start very close to v2 and then circle into v1. And this will be true regardless of any initial starting point. Oops, sorry. Got to get rid of that. And that's why we end up calling this a stable node in this particular case. Now, the stability, again, comes from the sign of the eigenvalues here. So there's our x equals 0. Every one of these, this is just called a node. It doesn't have a fancy descriptive title. It's just a node. Sometimes we call this a sink or a source. Now, in this particular case, if the lambda 1 and the lambda 2 are negative, we get what's called a sink. All the x will go to 0 as time goes to infinity. Everything will approach the origin and sink into it. But if the lambda 1 and the lambda 2 are both positive, it's a source. All the x will leave 0 as time goes to infinity. So a sink is stable, whereas a source is unstable. And they will have the same qualitative picture. You begin along one eigendirection and you end parallel to the other one. And it just depends on which one is dominant there. Now, the final situation here is when our eigenvalues have opposite signs. One's positive, one is negative. Now, in this situation, we've got an example here, -1 and 5. We have our two fundamental solutions, and we get a situation like this. What's important is we study the eigenvectors. And in the case of the eigenvectors here, we've got two of them again, v1 and v2. 1, 2, 1, 2. v1 is just along this diagonal. There's our v1. It will have a subspace. Its eigenspace is just that line. Whereas v2 ends up looking something like this. There's v2. Again, it's also a line. And what we want to do is look at the contribution for each term. And because they're equal in sign, it's going to be a lot easier to understand. As time goes to infinity, what's going to happen is that we are going to have a term that's dominant here. E to the 5t is dominant, right? Because this term, the e to the minus t, goes to 0. So that second contribution goes away, but the e to the 5t dominates. It will just become larger and larger and larger. All the trajectories are just going to be a very large scalar multiple of v1. So all the trajectories approach v1. So for large times, everything is going to want to get closer to the v1 eigenvector, regardless of where it starts from. But in this second situation, if we were to run the movie in reverse as time goes to negative infinity, e to the minus t dominates, and e to the 5t will go to 0. So all the trajectories in some way start parallel to V2. So eventually, if you were just to let the movie run fully forward and fully backward in time, everything will start parallel to V2, but end parallel to V1. And that's completely determined by the sign of the eigenvalues. You end up starting along the negative eigenvalue, and you end up finishing along the positive eigenvalue. If you were to start along one of the eigenvalues, you'll just end up going along that eigenvalue. The point here, x equals 0, this is what's called a saddle. And you can see it from the shape. You never make your way to the origin. You'll never be able to get there. You've got this bent shape like a saddle. So this covers all of the cases of the 2x2 phase plane analysis. This is important not so much for the linear systems themselves, it'll give you useful insight, but for down the road when we get to nonlinear systems.